Tonight, we're going to look back to a time when the universe was supposed to be young. A time before mature galaxies, before giant black holes, before the cosmic structures we see around us today had enough time to fully form. At least, that is what scientists expected. Then James Webb opened its golden eye and looked deeper than any telescope before it. It searched the darkness near the beginning of time and found something that did not seem ready to exist. Galaxies too bright, black holes too massive, structures too mature, tiny red objects hiding enormous power. And suddenly, the early universe did not look simple anymore. It looked crowded, awake, and impossible. Before we begin, if you enjoy quiet journeys into the deepest mysteries of space, take a moment to like the video or subscribe. It helps this channel reach more curious minds who still look into the dark and wonder what the universe is trying to tell us. Now, let's begin. Let's start with the telescope that was built to see the first light. Far from Earth, beyond the moon, beyond the familiar orbit of our planet, there is a machine floating in the darkness. It does not look like the telescopes most people imagine. It has no long white tube, no glass eyepiece, no lonely astronomer standing beside it under a mountain sky. Instead, it looks almost unreal. A wide golden mirror, made from 18 hexagonal segments, opened like a giant honeycomb flower. Beneath it, a vast silver sunshield stretches out in layers, thin and delicate-looking, like the sail of some ancient ship built not for oceans, but for darkness. It drifts quietly at a place called L2, about 1 million miles from Earth, where the gravity of the Sun and Earth allow it to stay in a stable position, always turned away from heat, always protected from the bright glare that would blind its instruments. This is the James Webb Space Telescope, and it may be one of the most important machines human beings have ever built. Not because it is large, though it is. Not because it is expensive, though it was. Not even because it is powerful, though it is more powerful than any space telescope before it. Webb matters because of what it was built to ask. What happened at the beginning? What did the first galaxies look like? When did the first stars ignite? How did darkness become light? These questions are not small scientific details. They are part of the deepest human story. Every civilization has wondered where everything came from. Ancient people told stories of creation, of light emerging from darkness, of worlds being shaped out of chaos. Modern science asks the same question with different tools. Not myths, not temples, not sacred fires, but mirrors, detectors, rockets, mathematics, and light. James Webb is one of those tools. It is not just a telescope. It is a way of looking backward. Because in space, distance and time are tied together. When you look at the moon, you see it as it was a little more than 1 second ago. When you look at the sun, you see it as it was about 8 minutes ago. When you look at a star hundreds of light years away, you are seeing light that began its journey before many people alive today were born. And when Webb looks at the most distant galaxies, it sees light that has traveled for billions of years. Light that left its source before Earth existed, before the sun existed, before our solar system had gathered from dust. This is what makes Webb feel almost impossible itself. It is a machine built by a young species on a small planet, designed to collect ancient photons from the edge of cosmic memory. Each faint point of light in its images may be an entire galaxy. Each smudge may contain billions of stars. Each red glow may be a message from a time when the universe was still learning how to become the universe we know. But Webb does not see the universe the way our eyes do. Our eyes see visible light, the narrow band of color from red to violet. That is the light of sunsets, fire, oceans, skin, leaves, and stars in the night sky. But the oldest light in the universe has been stretched. As space itself expands, light traveling through it is pulled into longer and longer wavelengths. Light that began as visible or ultraviolet becomes infrared by the time it reaches us. To see the early universe, you need to see in infrared. That is why Webb was built to be cold. Very cold. Heat gives off infrared radiation. A warm telescope would glow in the same kind of light it is trying to detect. It would be like trying to hear a whisper while standing beside a roaring engine. So Webb hides from the sun behind its enormous shield, keeping its instruments cold enough to sense the faint warmth of ancient light. It is listening with temperature, seeing with darkness, reading the universe in light human eyes were never meant to see. This is also why Webb can peer through dust. Cosmic dust blocks visible light, hiding young stars and forming galaxies behind thick clouds. But infrared light can pass through much of that dust, allowing Webb to see into places that were hidden from Hubble and other telescopes, so Webb can look in two directions at once. It can look far away, toward the beginning of time. And it can look deep inside dusty regions where stars and planets are being born right now. It is a telescope for origins. The origins of galaxies, the origins of stars, the origins of planets, and maybe, one day, the origins of life elsewhere. When Webb finally unfolded in space, it was like watching a very slow miracle. Every part had to work. The mirror had to open. The sun shield had to stretch. The instruments had to cool. The segments had to align with impossible precision. A failure in one step could have ended the mission before it truly began. There was no repair crew waiting nearby. No astronaut could simply fly out and fix it. Webb was too far away. It had to unfold itself. For days and weeks, the world watched as engineers sent commands into space and waited for confirmation. One movement at a time. One latch, one motor, one layer, one mirror segment, one adjustment after another. A machine made on Earth slowly becoming an eye for the universe. And when the first images came back, they felt almost unreal. Galaxies everywhere, sharp stars with bright diffraction spikes, nebulae filled with glowing gas, ancient light bent by gravity, clusters of galaxies acting like cosmic magnifying glasses. It was beautiful, but beauty was only the surface. Underneath those images was data, and inside the data were questions. Webb was not simply taking pictures for us to admire. It was measuring light, breaking it apart, studying its color, its redshift, its chemical fingerprints, its age, its distance. It was doing what it had been built to do, reading the oldest chapters of the universe. Scientists expected surprises. Every powerful telescope brings surprises. Hubble had changed astronomy before it. It revealed galaxies in places that looked empty. It measured the expansion of the universe. It showed star birth, star death, and deep fields filled with ancient galaxies. No one expected Webb to simply repeat what we already knew. But the kind of surprise Webb brought was different. It was not just that the early universe was visible. It was what the early universe looked like. Some galaxies seemed too bright. Some seemed too massive. Some looked as though they had built stars too quickly. Some objects were tiny and red, almost hidden, but possibly carrying the light of growing black holes. Some systems appeared more mature than scientists expected for a universe so young. And that is where the story becomes unsettling. Because Webb was not supposed to find nothing. Scientists knew the early universe had galaxies. They knew stars formed long ago. They knew black holes existed in distant cosmic history. But they expected a certain rhythm, a certain pace. A universe that began simply and grew more complex over time. Small structures first, then larger ones. Tiny galaxies merging into bigger galaxies. Stars forming, dying, enriching space with heavier elements. Black holes growing slowly through feeding and collisions. A young universe should look young. That was the expectation. But Webb began showing us that the beginning may have been more active, more crowded, and more efficient than many models predicted. It was like opening an old book to the first chapter and finding pages that seemed to belong much later. Not proof that everything we know is wrong. Not proof that the Big Bang did not happen. Not a reason to throw away all of cosmology. But a warning. A quiet warning from ancient light. The universe may have grown up faster than we thought. And if that is true, then Webb is not only showing us distant galaxies, it is showing us a missing part of the story. A chapter between darkness and structure, between the first stars and the first mature galaxies, where something happened quickly enough to make the young universe look older than it should. To understand why that matters, we have to follow Webb's gaze backward, not just across space, but toward the beginning of time itself. To understand why Webb's discoveries feel so strange, we have to understand what it means to look far away. Because in astronomy, distance is never only distance. Distance is time. Every time we look into space, we are looking into the past. This is one of those facts that sounds simple when you first hear it, but the more you sit with it, the more unreal it becomes. The light entering your eyes at night did not leave the stars at the moment you saw it. It traveled. It crossed emptiness. It moved through years, centuries, sometimes millions or billions of years before finally reaching Earth. The sky is not showing us the universe as it is now. It is showing us the universe as it was. The moon is close enough that its light takes only a little more than 1 second to reach us. If the moon suddenly vanished, we would not know for just over a second. The sun is farther. Its light takes about 8 minutes to reach Earth. Every sunrise is already 8 minutes old by the time it touches your face. That delay feels small, but then the scale begins to grow. Light from the nearest stars takes years to arrive. Light from some stars visible to the eye began its journey before the people watching it were born. Light from distant nebulae may have traveled for thousands of years, passing through space while civilizations rose and fell here on Earth. And then there are galaxies. When we look at the Andromeda Galaxy, we are seeing light that has traveled for about 2.5 million years. That light left Andromeda before modern humans built cities, before agriculture, before written language, before nearly everything we recognize as human history. And Andromeda is still nearby in cosmic terms. The galaxies James Webb was built to study are much farther, so far that their light has been traveling for most of the history of the universe. When Webb looks at some of the earliest galaxies, it is not seeing them as they exist today. It is seeing them as they were when the universe was young. Some of that light left its galaxy more than 13 billion years ago. It began moving across space before Earth existed, before the sun formed, before the Milky Way looked the way it does now. By the time that light reached Webb's mirror, the universe had changed completely. Stars had been born and died. Galaxies had merged. Planets had formed. Life had appeared on at least one small world. Human beings had evolved, looked upward, invented mathematics, built rockets, and placed a golden telescope in space to catch that ancient glow. There is something almost impossible about that chain of events. A photon leaves a young galaxy in the early universe. It travels through expanding space for billions of years, and finally, after crossing almost all of cosmic history, it lands on a mirror built by creatures who did not exist when the journey began. That is what Webb is collecting. Not just light, memory. And the deeper Webb looks, the earlier the memory becomes. But there is a problem. Ancient light does not arrive looking the way it looked when it began. The universe is expanding. Space itself is stretching. As light travels through expanding space, its wavelength stretches too. Blue light can become redder. Ultraviolet light can stretch into visible light. Visible light can stretch into infrared. The farther the light has traveled, and the more space has expanded during its journey, the more stretched that light becomes. This stretching is called redshift. Redshift is one of the main ways astronomers measure how far back in time they are looking. The more redshifted a galaxy's light is, the longer it has traveled, and the earlier in cosmic history that galaxy appears. This is why Webb sees in infrared. The first galaxies did not necessarily shine in infrared when their light began traveling, but after billions of years of expansion, that ancient light has been pulled into infrared wavelengths. A telescope designed mainly for visible light would miss much of it, or see only part of the story. Webb was designed to see the stretched light of the ancient universe, to catch what time and expansion have made invisible to ordinary eyes. This is also why Webb feels so different from a normal camera. It is not just collecting pretty images, it is measuring the universe's history. It separates light into colors and fingerprints. It asks how old a galaxy is, how far away it is, what elements are inside it, how quickly it forms stars, whether dust is present, and whether a hidden black hole may be feeding at its center. Each observation is a kind of detective work. A faint red dot in a Webb image might be a tiny galaxy, or a dusty star-forming system, or a young galaxy hiding an active black hole, or something more complicated than any single label can hold. That is part of what makes the early universe so difficult. The objects are faint, distant, and ancient. Their light is stretched, weakened, and sometimes magnified by the gravity of massive galaxy clusters between us and them. Scientists have to untangle all of this carefully before they can say what they are seeing. But even with that caution, Webb began revealing something powerful. The early universe was not empty, not quiet, not simple. It was already building. To understand the shock of that, we have to imagine the universe before galaxies. In the earliest moments after the Big Bang, the universe was hot, dense, and filled with energy. As it expanded, it cooled. Particles formed. Then atoms formed. For a long time, there were no stars, no galaxies, no planets, no heavy elements, no familiar structures, just darkness, gas, gravity, and time. This period is sometimes called the cosmic dark ages. The universe was not literally empty, but it had no stars to shine. It was filled mostly with hydrogen and helium, the simplest elements. Gravity was slowly working on tiny differences in density, pulling matter together. Slightly denser regions attracted more matter. Over time, those regions grew denser still. Slowly, the universe began preparing its first lights. The first stars must have been strange compared to many stars we know today. They formed from almost pure hydrogen and helium, without the heavier elements that later generations of stars would contain. They may have been enormous, hot, brilliant, and short-lived. They burned, changed the gas around them, exploded, and created the first heavier elements. From those first stars came the beginnings of cosmic chemistry. Carbon, oxygen, iron, silicon. The ingredients that would one day become dust, planets, oceans, and bodies. The first galaxies formed as gravity pulled stars, gas, and dark matter together. Small systems merged into larger ones. Over time, galaxies grew. They formed more stars. Their stars died and enriched them with heavier elements. Black holes formed and fed. Structures became more complex. This was the expected story. A gradual awakening. Darkness first, then the first stars, then small young galaxies, then larger galaxies built over time. The early universe was supposed to look like the beginning of construction, not a finished city. That is why Webb's discoveries felt so unsettling. It was looking into a time when cosmic structure should have been young, a time when galaxies should have been small, faint, and still assembling, a time before there had been enough generations of stars to create much dust or heavy elements, a time before black holes should have had long enough to grow into giants. And yet Webb began finding objects that seemed to push against that picture. Galaxies that looked surprisingly bright, objects that appeared compact but powerful, signs of rapid star formation, hints of black holes feeding earlier than expected. Distant systems that did not look as unfinished as many scientists had imagined. It was not that Webb found a universe with no explanation. It was that Webb found a universe moving faster than expected. A young universe that had already begun doing old things. This is the heart of the mystery. When we look far enough back, we expect to see beginnings. But Webb is showing us beginnings that are already complicated. The first chapters of the universe may have been busier, stranger, and more efficient than our models allowed. And that changes the feeling of cosmic history. The beginning was not empty silence, slowly becoming structure. It may have been a storm of formation. Stars igniting quickly. Gas collapsing violently. Black holes feeding in the dark. Galaxies assembling faster than expected. Dust and heavy elements appearing sooner than they should. The universe was young, but perhaps it was never simple. And to understand why that matters, we have to look at what scientists thought the early universe was supposed to be before Webb opened its eye and began reading the ancient dark. Before Webb showed us what was hiding in the ancient dark, scientists already had a story. Not a simple story, not a perfect story, but a powerful one. A story built from decades of observations, equations, simulations, and older telescopes looking deeper and deeper into space. It was the story of how the universe grew from almost perfect smoothness into the enormous cosmic web we see today. A universe filled with galaxies, stars, planets, black holes, dust, and light. And like every good scientific story, it had expectations. The early universe was supposed to look young. That seems obvious at first. A young universe should look young in the same way a young forest looks young. The trees should be small. The roots should not yet be deep. The canopy should not yet be thick enough to block the sky. Everything should still be forming, still fragile, still unfinished. For the universe, that meant the first galaxies should be small. They should be faint. They should be messy. They should be made mostly of simple gas, with very few heavy elements, because heavy elements had not had much time to exist yet. They should be places where stars were just beginning to form in serious numbers. They should not already look like the large, mature galaxies we see much later in cosmic history. That was the expectation. And it came from the way structure forms. After the Big Bang, the universe was not filled with galaxies. It was filled mostly with hydrogen, helium, dark matter, radiation, and tiny differences in density. Some regions were slightly denser than others. Not by much, but gravity is patient, and over time, those tiny differences mattered. A slightly denser region pulled in more matter. Then, because it had more matter, it pulled even harder. Slowly, invisible dark matter gathered into large halos, like gravitational wells in space. Normal matter, the gas that could form stars, fell into those wells. The gas compressed, heated, cooled, fragmented, and eventually formed the first stars. But this process was not expected to happen instantly. Gravity may be patient, but it still needs time. Gas must gather. Stars must form. Stars must live. Stars must die. Their explosions must scatter heavier elements. Those elements must mix into new clouds. New stars must form from enriched gas. Small galaxies must collide and merge into larger galaxies. Black holes must form, feed, and grow. Everything builds on what came before. That is why the early universe was expected to be simple. Not because nothing was happening, but because there had not been enough time for many generations of cosmic construction. The first stars were probably very different from stars like the Sun. They formed from almost pure hydrogen and helium. They may have been massive, brilliant, unstable, and short-lived. Because they lacked heavier elements, they may have burned hotter and died more violently. When they died, they helped create the first heavier elements, the first carbon, oxygen, silicon, iron, and dust. Only after stars died could later stars and planets become more chemically rich. That means early galaxies should have carried the signs of youth: less dust, fewer heavy elements, more chaotic star formation, smaller size, less mature structure. In a sense, scientists expected Webb to see the universe before it had finished learning how to make complexity. It was not supposed to see nothing. That is important. Sometimes people talk about Webb as if scientists expected the early universe to be empty, and then Webb shocked everyone by finding galaxies. That is not quite right. Scientists absolutely expected early galaxies. They expected star formation. They expected black holes. They expected strange, young, distant objects. But they expected them to fit a timeline, a rhythm, a reasonable pace of growth. You can think of it like entering a city under construction. You expect cranes. You expect scaffolding. You expect foundations. You expect half-built towers, dust, noise, and workers moving everywhere. What you do not expect is to walk into the construction site and find fully lit skyscrapers already standing, with roads, windows, power lines, and traffic. That is what some of Webb's early results felt like. Not proof that the city could not exist, but proof that construction may have started earlier, moved faster, or followed a different plan than expected. Before Webb, older telescopes had already shown that the distant universe was full of galaxies. Hubble had looked into tiny dark patches of sky and found thousands of galaxies where the eye saw nothing. It had taken deep field images that changed how humans imagined space. It had shown that even the emptiest-looking darkness was crowded with ancient light. But Hubble was limited. It could not see the earliest infrared light as clearly as Webb. It could push far, but not far enough to easily study the first galaxies in detail. It gave us hints of cosmic dawn, but Webb was designed to enter that dawn more directly. So scientists built models. They used what they knew about dark matter, gas, star formation, gravity, and cosmic expansion. They simulated the early universe on powerful computers. They watched virtual matter collapse into halos. They watched stars form in clusters. They watched small galaxies merge into larger ones. They tested how quickly galaxies could grow, how bright they should be, and how common massive early objects should be. These models were not guesses in the ordinary sense. They were grounded in physics. But models are still models. They are maps, not the territory. And the early universe is a territory we had barely visited. Before Webb, there were many things scientists could not know clearly. How efficient was early star formation? How quickly did gas cool? How much dust could form after the first supernovae? How rapidly could black holes feed? Did some black holes form from the deaths of massive stars? Or did they begin as much larger seeds from collapsing gas clouds? How strongly did young stars and black holes affect the gas around them? Each question matters. Change one answer, and the young universe grows differently. Maybe galaxies brighten faster. Maybe black holes appear earlier. Maybe dust forms sooner. Maybe stars are born in bursts more intense than expected. Maybe small systems merge more quickly. Maybe ancient light fools us because dust, black holes, and young stars can make a galaxy look older or heavier than it truly is. This is why Webb's discoveries are both thrilling and difficult. When it finds something that looks impossible, scientists do not immediately throw away everything. They ask, is it really as distant as it appears? Is it truly massive? Is the light coming from stars or from a feeding black hole? Is dust changing its color? Is gravity magnifying it? Are we seeing one object or several? Are our assumptions about the first stars wrong? The word impossible is emotional. The science is more careful. But the feeling behind that word is real, because Webb began finding things that pressed against the edges of expectation. Bright galaxies in the first few 100 million years. Compact red objects that did not fit neatly into simple categories. Evidence that some black holes may have grown extremely quickly. Hints of chemical enrichment and dust earlier than expected. Structures that suggested the young universe was not as slow or simple as our best models had imagined. It was not one discovery alone. It was the pattern. Again and again, Webb seemed to be saying that the first era of galaxy formation was more intense than we thought. The universe was not patiently assembling in the way we pictured. It was rushing. Or at least, parts of it were. This does not mean the Big Bang is wrong. It does not mean cosmology has collapsed. It does not mean scientists were foolish before Webb. It means the universe is more detailed than the sketches we made before we could see it clearly. That is how science often changes. Not by one dramatic explosion, but by pressure. A telescope looks deeper. The data becomes sharper. Old assumptions begin to bend. Questions multiply. And slowly, the story becomes richer. Before Webb, the early universe was supposed to be a dim construction site filled with small beginnings. After Webb, that picture is still there, but it is no longer enough. Some parts of the construction site look strangely advanced. Some lights are already burning too brightly. Some engines are already running too powerfully. Some corners of the young universe seem to have matured in the dark before anyone expected them to. And that brings us to the first major mystery Webb placed in front of us. The galaxies that seem to arrive too early. The galaxies that seem to arrive too early. That was one of the first great shocks Webb gave us. Not because astronomers believed there should be no galaxies in the early universe. They knew galaxies had to exist there. They knew the first structures formed long ago. They knew that if Webb looked deeply enough, it would find faint systems shining from near the beginning of time. But some of what Webb found did not feel faint enough. Some of it did not feel small enough. Some of it looked as though the universe had built too much, too quickly. Imagine looking through an old family album. You turn to the first few pages, expecting to see a child just beginning to grow. But instead, in one of those early photographs, the child already looks older, taller, stronger, almost as if several years are missing between one page and the next. That was the feeling. The early universe was supposed to be young, and it was young. But Webb began finding galaxies whose light came from a time when the universe was only a few 100 million years old, and some of them looked surprisingly bright. Brightness matters. In deep space, brightness can tell us something about how many stars a galaxy contains, how quickly it is forming stars, whether dust is changing the light, and whether a black hole might be feeding at its center. A bright early galaxy can mean many things. It might be forming stars at an intense rate. It might contain more stellar mass than expected. It might have less dust blocking its light than scientists assumed. Or it might be powered partly by an active black hole, making it appear brighter than stars alone would allow. But whichever answer is true, the message is the same. The early universe was active, maybe more active than expected. In the first Webb deep fields, astronomers saw tiny red smudges that appeared to be extremely distant galaxies. Some of them were candidates from very early cosmic time, possibly only a few 100 million years after the Big Bang. Their light had been stretched into infrared by the expansion of the universe, exactly the kind of ancient signal Webb was designed to detect. At first, some estimates made these galaxies look astonishingly massive. Too massive, some headlines said. Too bright. Too old. Too mature. There was excitement, confusion, and caution all at once. Because if those early estimates were correct, then the universe had produced large galaxies faster than many models allowed. Gravity would have needed to pull gas together quickly. Stars would have needed to form efficiently. Matter would have needed to organize itself into luminous systems while the universe was still in its cosmic childhood. That seemed difficult. Not impossible in the absolute sense, but difficult enough to make scientists look again. And looking again is exactly what science does. The first data from a distant galaxy can be uncertain. A red color may suggest great distance, but dust can also redden light. A galaxy may look massive because of the way its stars shine, or because a hidden black hole is adding light. Its distance may need confirmation through spectroscopy, where Webb breaks the light apart and measures its fingerprints more precisely. So after the first wave of excitement, astronomers began checking the objects carefully. Some early galaxy candidates turned out to be less extreme than they first appeared. Some masses were revised downward. Some objects were better understood once scientists had more detailed observations. Some of the tension with cosmological models softened, but the mystery did not disappear. That is important. The lesson was not, Webb was wrong. The lesson was more subtle. Webb was showing that the young universe may have been better at making bright galaxies than many expected. Even after corrections, Webb continued to find many early galaxies. It continued to show that star formation was already happening vigorously at very high redshifts. It continued to suggest that galaxy growth in the first few 100 million years may have been fast, efficient, and complicated. The impossible thing was not one single galaxy. It was the pattern. Again and again, Webb looked into ancient darkness and found light. Too much light, in some places, for comfort. Galaxies are not simple objects. They are cities of stars, gas, dust, dark matter, and sometimes central black holes. To build one, the universe needs structure. Dark matter must gather first, forming invisible halos. Gas must fall into those halos. The gas must cool enough to collapse. Stars must ignite. Some of those stars must die and enrich the galaxy. The system must keep growing through more gas, more star formation, and mergers with other small galaxies. That takes time. And the early universe did not seem to have much time to spare. When we say a galaxy existed only a few 100 million years after the Big Bang, that may still sound like a long time. 100 million years is far longer than human history. It is longer than the time since dinosaurs disappeared. It is a massive length of time by any earthly standard. But for building a galaxy, it is fast. Very fast. Especially if that galaxy is bright, compact, chemically active, or full of stars. The universe had to move from hot early plasma to neutral gas, to the first stars, to the first galaxies, to systems bright enough for Webb to detect across almost all of cosmic history. That is an enormous transformation. And Webb is showing us that transformation may have happened with surprising speed. There are several possible reasons. Maybe the first galaxies formed stars more efficiently than nearby galaxies do today. In the modern universe, not all gas turns into stars quickly. Gas can be heated, blown away, stirred by supernova explosions, or disrupted by radiation. But in the early universe, conditions may have allowed gas to collapse in intense bursts, creating stars rapidly. Maybe the first stars were different. If they were massive and brilliant, they could make young galaxies shine strongly, even without as much mass as first assumed. A galaxy might look bright, not because it had an impossible number of stars, but because its stars were unusually luminous. Maybe dust confused the picture. Dust can hide some light and redden other light. It can make a galaxy look older or more distant if scientists are not careful. But dust itself is also interesting, because dust requires previous generations of stars. If dust appears early, that means stars had already lived and died quickly. Maybe black holes contributed. A feeding black hole can produce enormous energy from a small region. If a young galaxy hides an active black hole, it may appear brighter or stranger than a galaxy powered only by stars. Maybe dark matter halos formed earlier or more efficiently in some regions than expected. The universe was not perfectly uniform. Some places were denser than others. In especially dense regions, structure may have grown faster. Or maybe our models need more detail. That is not failure. That is discovery. The models were built from the best information available before Webb. But Webb is entering a part of cosmic history where direct observation was limited. It is like sailing into a foggy coastline that maps only roughly described. The map may show the continent correctly, but not every cliff, river, storm, or hidden harbor. Webb is giving the map detail. And some of that detail is surprising. The emotional power of these early galaxies comes from what they imply. If galaxies formed faster than expected, then the universe's first stars may have ignited earlier or in more intense bursts. The first black holes may have formed sooner. The first heavy elements may have spread more quickly. The Dark Ages may have ended with more violence and speed than we imagined. The beginning was not slow and gentle. It may have been bright, crowded, and fierce. A storm of newborn stars, small galaxies colliding, gas collapsing, radiation flooding into darkness, black holes feeding in hidden centers, the first islands of light growing rapidly inside an ocean of hydrogen. And after more than 13 billion years, Webb is catching the faint remains of that ancient fire. This is why the phrase, "arrived too early," feels so powerful. These galaxies did not actually arrive early from their own point of view. They formed when they formed, according to the real physics of the universe. The problem is with our expectation. We thought we understood the timing well enough. Webb is telling us the timing may be different. The universe was not waiting for our models. It was doing what it does. Building, burning, changing, faster than we thought in places we had barely seen. And scattered among those early galaxies, Webb found another class of objects that made the mystery even deeper. They were small. They were red. They looked almost harmless. But inside some of them, there may be something enormous hiding in the dark. They were small. They were red. They looked almost harmless. But inside some of them, there may be something enormous hiding in the dark. When James Webb began looking into the early universe, astronomers noticed a strange population of compact red objects scattered through the ancient light. In images, They did not look dramatic at first. They were not grand spiral galaxies stretching across space. They were not enormous glowing nebulae. They were not bright nearby stars with long diffraction spikes. They were tiny, faint, red. Easy to overlook if you did not know what you were looking at. But science often changes because of things that look small at first. These objects became known by a simple nickname, little red dots. The name sounds almost gentle, but the mystery behind them is not gentle at all. Because some of these little red dots may be telling us that the early universe was forming galaxies, stars, and black holes in ways we still do not fully understand. At first glance, a red dot in a Webb image can mean several things. It may be red because it is extremely far away. As the universe expands, light from distant objects stretches into longer wavelengths. The farther the object, the more stretched the light becomes, and the redder it appears. For the most distant objects, light that began as ultraviolet or visible may arrive at Webb as infrared. So redness can be a sign of age, a sign that the light has crossed billions of years. But redness can also come from dust. Dust in a galaxy can absorb shorter wavelengths and let redder light pass through. A dusty galaxy can look old or distant even if the full story is more complicated. Dust can hide star formation. It can disguise the true shape of a galaxy. It can make something young look mature, or something closer look farther away than it really is if scientists are not careful. And redness can come from stars themselves. A galaxy filled with older stars may appear redder than one filled with young, hot, blue stars. Different populations of stars leave different fingerprints in the light. But there is another possibility, a more unsettling one. Some of these red dots may be hiding active black holes. A black hole itself gives off no light. That is what makes it black. But the material falling toward a black hole can become extremely hot. Gas spirals inward, compressed and accelerated by gravity, forming a glowing disk around the black hole. Before some of that matter disappears forever, it can shine with enormous power. A feeding black hole can outshine the stars around it. It can make a small region of space look strangely bright. It can change the color of the light. It can hide inside what appears to be a compact young galaxy. And if some little red dots are powered by early black holes, then Webb has uncovered something deeply important. It may have found signs of black holes growing in the young universe far earlier, and perhaps far more commonly than expected. This matters because black holes are not easy to grow. A small black hole can form when a massive star dies. But to become supermassive, millions or billions of times the mass of the Sun, it must feed. It must pull in gas. It may merge with other black holes. It must grow across time. Time is the problem. When Webb looks at some of these early objects, it is looking back to a universe that may have been only hundreds of millions of years old. That sounds long by human standards, but for growing a giant black hole, it is not very long at all. So if a little red dot contains a massive feeding black hole, it raises a question. How did it get so big so quickly? Was the black hole born from the death of one of the first massive stars, then somehow fed at an extraordinary rate? Did it begin as a much larger seed, formed by the direct collapse of a huge gas cloud? Did black holes grow faster in the early universe because gas was denser and easier to feed on? Or are we misunderstanding what these objects are? That is the beauty and difficulty of the little red dots. They do not offer one easy answer. They sit at the edge of several possibilities. They may be compact galaxies packed with stars. They may be dusty star-forming systems. They may be young galaxies containing hidden active galactic nuclei. They may be a mixture of all of these. And perhaps that is the point. The early universe may not have built things in the neat categories we prefer. We like to separate objects. Galaxy here. Black hole there. Star-forming cloud here. Dusty system there. But in the first billion years, everything may have been tangled together. Galaxies were young. Gas was abundant. Stars formed in violent bursts. Black holes may have fed rapidly. Dust and heavy elements were beginning to appear. Radiation filled small systems from many sources at once. A little red dot may not be one simple thing. It may be a whole early cosmic environment compressed into a tiny glow. a young galaxy, a hidden engine, a swarm of stars, a cloud of dust, a black hole feeding in the center. All of it so far away that, to Webb, it becomes only a red point in the dark. There is something humbling about that. An object that may reshape our understanding of galaxy formation can appear to us as a dot, a few pixels, a faint color difference, a small signal in the data that requires careful study to interpret. But those pixels may contain billions of stars, or a black hole millions of times the mass of the Sun, or the evidence of processes that began when the universe was still young. This is why Webb's images are not only beautiful, they are dangerous to our assumptions. They remind us that the universe does not need to appear dramatic to be profound. Sometimes the deepest mystery is not the brightest object in the frame. Sometimes it is the tiny red speck that should not be as powerful as it is. Scientists study these objects using spectroscopy. Instead of simply taking an image, Webb can split the light into its component wavelengths. This creates a spectrum, a kind of barcode of the object's light. Inside that barcode are clues: redshift, chemical elements, dust, gas motion, star formation, and possible black hole activity. A spectrum can tell astronomers whether the object is truly distant. It can reveal emission lines from glowing gas. It can show whether radiation is coming from young stars or from a harder, more energetic source like an active black hole. It can turn a red dot into a story. But the story is still being written. Some little red dots may turn out to be less massive than first thought. Some may be explained by unusual star populations. Some may indeed contain active black holes. Others may remain strange for years, waiting for more data, deeper observations, and better models. That is how the edge of knowledge feels. Not clear, not finished. Full of objects that seem to be saying, "You have not understood us yet." The emotional power of the little red dots comes from their silence. They do not look like monsters. They do not announce themselves. They do not dominate the image. They sit quietly in the ancient dark, carrying light that began traveling before Earth existed. And when that light finally reaches us, it suggests that the early universe may have been hiding enormous activity inside very small packages. That is unsettling, because if black holes were already growing inside some of these compact early systems, then the relationship between galaxies and black holes may be different from what we imagined. Maybe black holes did not always grow slowly after galaxies formed. Maybe in some places, black holes and galaxies grew together. Maybe in some cases, the black hole came first. Maybe the seed of darkness helped shape the island of stars around it. And if that is true, then the early universe was not simply a place where stars gathered into galaxies. It was also a place where gravity formed deep wells, where gas fell violently inward, where hidden engines turned on before the universe had fully settled into its later shape. A little red dot may be small only from our point of view. From inside its own ancient time, it may have been a storm, gas rushing inward, stars forming in dense clusters, dust glowing, radiation blasting through young space. A black hole feeding at the center, growing in a universe still young enough that its size should make us uncomfortable. That is why the next question becomes unavoidable. If these little red dots are hiding black holes, or even if only some of them are, then Webb has led us to one of the deepest problems in modern astronomy. How did the first black holes grow so fast? How did the first black holes grow so fast? That question sits at the center of one of Webb's most unsettling discoveries, because black holes are not supposed to become giants overnight. They can grow, yes. They can feed. They can swallow gas, dust, stars, and sometimes merge with other black holes. Across enough time, they can become enormous. At the centers of many galaxies, including our own Milky Way, there are supermassive black holes containing millions or even billions of times the mass of the Sun. But those black holes are usually found in galaxies that have had a long time to evolve. They sit inside systems shaped by billions of years of gravity, collisions, star formation, and cosmic history. The early universe was different. It was young. It was still building its first large structures. And yet Webb has found signs that massive black holes may have already been feeding when the universe was only a fraction of its current age. That is the problem. A black hole is simple in one way and deeply mysterious in another. It is a region where gravity becomes so strong that nothing, not even light, can escape once it crosses the event horizon. From the outside, a black hole may seem like a dark absence, a hole in reality, a place where matter disappears from view. But black holes are not always quiet. When gas falls toward them, it does not usually fall straight in. It spirals. It forms a disk. Friction and gravity heat the material until it glows. The region around the black hole can become one of the brightest sources of energy in the universe. This is called an active galactic nucleus when it happens at the center of a galaxy. A feeding supermassive black hole can shine across cosmic distances. It can send out radiation powerful enough to affect the galaxy around it. It can heat gas, drive winds, slow star formation, or perhaps help shape the growth of its host. So when Webb sees signs of active black holes in the early universe, it is not finding small details. It is finding engines, ancient engines, engines that seem to have turned on very early. The difficulty is growth. If the first black holes formed from the deaths of the first massive stars, they may have started with tens or hundreds of solar masses. That is already large compared to ordinary objects, but tiny compared to supermassive black holes. To reach millions or billions of solar masses, they would need to feed. And feeding has limits. A black hole cannot always swallow matter as fast as it wants. As material falls in, it releases radiation. That radiation pushes outward. If the black hole feeds too quickly, the energy coming from the hot gas can push nearby material away, slowing the feeding process. There is a balance between gravity pulling matter in and radiation pushing matter out. This creates a kind of speed limit for growth. So if a black hole is already enormous, very early in cosmic history, scientists have to ask how it broke, avoided, or stretched that limit. Did it feed constantly at the maximum possible rate? Did it feed even faster in short, violent bursts? Did it begin from a seed much larger than the death of an ordinary star could provide? Or was the early universe simply better at growing black holes than we thought? One idea is that the first black hole seeds were born from massive stars. The first stars may have been much larger than many stars today because they formed from simple hydrogen and helium without heavier elements. Some of them may have lived fast, died violently, and left behind black holes. But even then, the numbers are difficult. A small seed needs time to become a giant. Another idea is more dramatic. Maybe some black holes formed by direct collapse. In this scenario, a huge cloud of gas in the early universe collapses almost directly into a black hole without first forming a normal star. Instead of beginning with tens of solar masses, the black hole might begin with thousands, tens of thousands, or even more. A much larger starting point would make it easier to explain how supermassive black holes appeared so early. This would mean that some black holes were born big, not grown slowly from small stellar remnants, but formed as heavy seeds in dense regions of primordial gas. If Webb is seeing evidence for this, then the early universe was not just building galaxies quickly, it was building darkness quickly too. There is also the possibility of dense star clusters. In crowded early environments, massive stars and smaller black holes may have collided and merged, building larger black holes step by step. These clusters could act like nurseries for black hole growth, where gravity brings objects together again and again. Or perhaps gas in the early universe flowed inward more efficiently than expected. Young galaxies may have been rich in cold gas. Their centers may have been chaotic, dense, and violent. If enough material poured into the middle, black holes could feed rapidly, surrounded by enormous reservoirs of fuel. Each answer changes the story. If black holes started from massive seeds, then our picture of the first structures must include rare, direct collapse events. If they grew by extreme feeding, then early galaxies were more efficient at funneling gas into their centers than expected. If black holes and galaxies grew together, then they may have shaped each other from the beginning. And if black holes sometimes appeared before the galaxies around them fully formed, then the order of cosmic construction becomes stranger. We usually imagine a galaxy first, then a black hole growing at its center. But maybe, in some places, the black hole was not a passenger. Maybe it was one of the builders. A deep gravitational center forming early, pulling gas inward, heating it, shaping the young system around it. This is why early black holes feel so important. They are not only objects, they are clues about how structure began. A supermassive black hole in the early universe is like finding a tree with a thick trunk in a forest that was supposed to have just sprouted. You can explain it, perhaps, but you have to change the story of how quickly that forest grew. And Webb is finding more of these clues. Some come from the little red dots. Some come from distant quasars. Some come from galaxies whose light carries signs of highly energetic radiation. In each case, scientists ask whether young stars alone can explain what they see, or whether something harder and more powerful must be present. Sometimes the answer may be stars, sometimes dust, sometimes measurement uncertainty. But sometimes the answer may be a black hole feeding in the ancient dark. And that idea changes the feeling of the early universe. It was not only a place of first light, it was a place of first hunger. Gas falling inward, stars igniting and dying, gravity digging deep wells in space, black holes forming, feeding, merging, and growing while the universe was still young. There is something almost mythic about that image. Before planets, before life, before anything familiar, the universe was already creating objects that could swallow light. Darkness did not wait for the universe to become old. It appeared early, perhaps side by side with the first galaxies. And in some cases, it may have grown faster than expected. This does not mean the universe is broken. It means the beginning was more violent, more efficient, and more creative than our simpler models allowed. The early cosmos may have had places where gas collapsed with terrifying speed. Places where the first stars lived and died in quick succession. Places where black holes were fed by dense streams of matter, hidden inside small red galaxies that Webb now sees as faint dots. And if those black holes were already shaping their surroundings, then galaxies were never just collections of stars. They were ecosystems of light and gravity. Stars made elements. Gas made stars. Black holes fed on gas. Radiation pushed back. Gravity pulled everything together again. Even at the beginning, the universe may have been a struggle between collapse and explosion, darkness and light, growth and destruction. That is why Webb's early black holes are so unsettling. They suggest that some of the most powerful objects in the modern universe were not late arrivals. They were present near the opening chapters, growing in shadows we are only now beginning to see. But Webb did not only find brightness and hidden engines, it also began to reveal something just as surprising in another way. Shape, structure, order. In places where the universe was expected to be young and chaotic, Webb sometimes found systems that seemed more organized than they should be. And that leads to the next mystery. A universe that may have become structured too quickly. A universe that may have become structured too quickly. That is another part of Webb's mystery. Because the early universe was not only expected to be young in age, it was expected to be young in shape. Messy, turbulent, unsettled. A place where gas was still falling into dark matter halos, where the first stars were forming in bursts, where small galaxies were colliding, merging, breaking apart, and growing into larger systems. It should have been full of motion and violence, but not necessarily full of order. Order takes time. At least, that was the expectation. When we look at many galaxies in the nearby universe, we see structure that feels almost architectural. Spiral galaxies have wide, graceful arms. Disk galaxies rotate like enormous wheels. Elliptical galaxies glow with older stars, shaped by mergers and long histories. Barred galaxies have central structures that guide gas and stars. Some galaxies show rings, lanes of dust, organized star-forming regions, and patterns that suggest billions of years of evolution. These shapes are not decorations. They are records. A galaxy's structure tells a story about its past, how it formed, how it merged, how much gas it contains, how stars move through it, how gravity has shaped it over time. A calm rotating disk suggests a galaxy has settled. A spiral pattern suggests waves of density moving through the disk. A chaotic shape may suggest collisions, recent mergers, or violent star formation. So when astronomers look far back in time, they expect younger galaxies to look less settled, more irregular, more clumpy, more disturbed, and many of them do. The early universe is full of strange shapes, compact systems, merging galaxies, and irregular structures. Webb has seen that too. It has revealed galaxies that look like glowing knots of star formation, tiny systems still assembling themselves in the ancient dark. But the surprise is that this is not the whole story. Some early galaxies appear more organized than expected. Some seem to have disks. Some show hints of rotation. Some appear compact but already structured. Some look as if they have reached a level of maturity that feels uncomfortable for their age. Not always fully mature in the way a nearby spiral galaxy is mature. Not necessarily calm in every detail, but organized enough to raise questions. How did that order form so quickly? How did gas settle into rotating structures so early? How did stars arrange themselves into systems that do not look as chaotic as expected? If a galaxy exists when the universe is only a fraction of its current age, and yet already shows signs of ordered motion or mature structure, then something in the early universe was efficient. Maybe too efficient for our older assumptions. One possible answer is that galaxies can settle faster than we thought. In dense regions of the early universe, gas may have flowed along cosmic filaments into young galaxies. These streams of gas could feed star formation and help build disks quickly. Instead of growing only through chaotic mergers, some galaxies may have received smooth flows of material that allowed them to organize earlier. Another possibility is that our view is biased. Webb may be especially good at finding the brightest, most active, most unusual early galaxies. The objects we notice first may not represent the average young galaxy. They may be the exceptional ones, the cosmic overachievers. In a universe with countless galaxies, even rare early structures can appear if a telescope is powerful enough to find them. But even rare objects matter, because they show what the universe is capable of. A single, surprisingly organized early galaxy does not mean every model is wrong, but a growing population of early structured objects means scientists have to ask whether galaxy formation had more pathways than they once believed. Maybe some galaxies form slowly, maybe some form violently. Maybe some form in dense cosmic neighborhoods where gravity works quickly. Maybe some are shaped by black holes, gas flows, and starbursts in ways that allow order to appear early. The early universe may not have followed one simple timeline. It may have been a place of variety. Some galaxies were chaotic sparks. Some were growing disks. Some were compact red systems hiding black holes. Some were dusty star factories. Some were already beginning to take on forms that feel surprisingly familiar. This is what Webb keeps doing. It takes the simple picture and makes it crowded, more complicated, more alive. Before Webb, we had a sketch. Darkness. First stars. Small galaxies. Mergers. Growth. Larger galaxies. Black holes. Dust. Structure. After Webb, the order is not so neat. The first galaxies may have formed in many different ways. Some may have built stars rapidly. Some may have grown around heavy black hole seeds. Some may have been bright because of unusual early stars. Some may have been shaped by streams of cold gas. Some may have looked old because dust and hidden engines changed their light. Some may truly have been massive earlier than expected. The universe was not one story. It was many stories unfolding at once. That is why the phrase "too organized" matters. It does not mean the universe broke its own rules. It means we may not yet understand how flexible those rules are under extreme early conditions. Think of a stormy ocean at night. From far away, you might expect only chaos, waves, foam, wind, darkness. But if lightning flashes, you may see patterns, currents, spirals, lines of motion, shapes forming and dissolving in the water. The storm is still violent, but it is not random. The early universe may have been like that. Violent, yes. Chaotic, yes. But also guided by gravity, dark matter, gas flows, radiation, and time. Even in its youth, the universe was not formless. It had hidden structure. The cosmic web was already pulling matter along invisible threads. Dense regions were already becoming gathering places. Gravity was already writing patterns into the dark. Webb is seeing those patterns earlier than we expected, and each one asks us to revise the timeline. Not necessarily by throwing it away, but by adding detail, more pathways, faster growth, more efficient star formation, earlier black hole activity, more rapid chemical enrichment, different kinds of early galaxies than we imagined before we could see them clearly. There is a quiet emotional weight in this, because humans often imagine the beginning of things as simple. The beginning of a life, a civilization, a planet, a universe. We picture something small and clean, something that becomes complex only later. But Webb is showing us that the beginning of the universe may have been complex almost from the moment light began gathering into structure. The beginning was not empty. It was not calm. It was not waiting patiently. It was already moving in many directions. The first stars may have been exploding while other stars were forming. The first black holes may have been feeding while young galaxies were still assembling. Gas may have been streaming along cosmic filaments. Dust may have been appearing in places where stars had already died. Small systems may have been merging. Disks may have been settling. Radiation may have been clearing the fog of neutral hydrogen. The young universe was not a silent nursery. It was a construction site during a storm. And Webb is standing at the edge of time, watching the lightning reveal shapes inside it. This is why the discoveries feel impossible. Not because order cannot exist early, but because order appearing early forces us to ask how much of the first universe we have been missing. Maybe the first billion years were not a slow, gentle introduction to cosmic history. Maybe they were one of the most important, violent, and productive eras the universe ever had. An era where the first stars, galaxies, black holes, dust, and structure all began pushing against each other at once. And we are only now beginning to see it. But to understand these early objects, Webb must do more than look at their shapes. It must read their light. Because ancient light carries messages, and those messages have been stretched by the expansion of space for almost the entire age of the universe. To understand what Webb found, we have to understand the redshifted messages from the dark. To understand what Webb found, we have to understand the redshifted messages from the dark. Because ancient light does not come to us unchanged. It travels, it stretches, it fades. It carries the memory of a universe that no longer looks the way it did when that light began its journey. Every distant galaxy is sending us a message, but it is not a message written in words. It is written in color, brightness, wavelength, chemistry, motion, and time. Webb's job is to collect that message, separate it carefully, and ask what it means. At first, light seems simple. A star shines. A galaxy glows. A telescope receives the light. But between the source and the telescope, the universe itself gets involved. Space is expanding. Not expanding into something, like smoke spreading into a room, but expanding everywhere. The distances between faraway galaxies grow as space stretches. And as light travels through that expanding space, the light stretches with it. A wave of light has a wavelength. The distance between one crest and the next. Blue light has a shorter wavelength. Red light has a longer wavelength. Infrared light is longer still, beyond what human eyes can see. When light from a distant galaxy travels for billions of years through expanding space, its wavelength becomes longer. It shifts toward the red end of the spectrum. If it travels far enough, it shifts beyond visible red and into infrared. This is redshift. It is one of the most important ideas in astronomy. Redshift turns light into a clock. The more stretched the light is, the farther it has usually traveled, and the older the image we are seeing. A highly redshifted galaxy is not merely far away. It is young from our point of view, because we are seeing it as it was long ago. This is why Webb was built for infrared. The earliest galaxies are not invisible because they do not shine. They are difficult to see because their light has been stretched by the age and expansion of the universe. Much of the light that began as energetic ultraviolet or visible radiation now arrives as infrared. To catch the universe's first galaxies, a telescope must be sensitive to that ancient stretched glow. Hubble could see far. It gave us some of the deepest views humans had ever known. But Webb was designed to go further into this red-shifted darkness. Its golden mirror gathers faint infrared light. Its instruments are cooled to extreme temperatures so they do not drown the signal in their own heat. Its detectors can sense light that has crossed nearly all of cosmic history. And when Webb sees a tiny red object, scientists begin asking careful questions. How red is it? Is the redness caused by distance? Or dust? Or old stars? Or a black hole? This is where the work becomes delicate. A red color alone is not enough. Imagine seeing a small red light through fog. It might be far away. Or it might be close, but dimmed and reddened by dust. Or it might be part of something else entirely. Without more information, color can mislead. The same is true in the deep universe. A galaxy can look red because it is extremely distant. But a dusty galaxy closer to us can also look red. A galaxy filled with certain types of stars can appear redder than expected. A feeding black hole can change the light. Gravitational lensing can magnify an object, making it seem brighter than it would otherwise appear. So Webb does not only take images, it takes spectra. A spectrum is what happens when light is split apart into its many wavelengths. Like a prism spreading sunlight into a rainbow, Webb can separate the light from a distant object and reveal hidden patterns inside it. But these patterns are far more than colors. They are fingerprints. Certain elements absorb or emit light at specific wavelengths. Hydrogen leaves signatures. Oxygen leaves signatures. Carbon, nitrogen, neon, helium, and other elements leave their own clues. Hot gas around young stars produces certain emission lines. Gas near an active black hole can produce stronger, more energetic signatures. Dust changes the shape of the light. The motion of gas can broaden or shift features in the spectrum. A spectrum lets scientists read the object. It can tell them how far away it is. It can show whether the object is forming stars. It can reveal whether heavier elements are present. It can suggest whether a black hole is feeding. It can turn a vague red dot into a physical story. This is why some early claims from Webb became more careful over time. At first, a very red object in an image may look like a record-breaking ancient galaxy. But once scientists collect a spectrum, the story can change. Some objects are confirmed as truly distant. Others turn out to be closer, dustier, or different from what their first colors suggested. That does not make the first observations meaningless. It makes them the beginning of the process. Images open the door. Spectra tell us what is inside. And Webb's spectra have become some of the most important messages ever read from the early universe. They show that galaxies existed when the universe was very young. They show that star formation was already active. They help measure the pace of growth. They reveal signs of elements that had to be made inside stars. They help identify possible early black holes. They allow scientists to separate appearance from reality. But sometimes reality is still surprising. Because when Webb confirms that an object is truly distant and still bright, or chemically active, or compact and powerful, the mystery becomes stronger. The object can no longer be dismissed as a trick of color alone. Its light has been measured. Its redshift is real. Its place in cosmic time becomes harder to ignore. That is when the ancient message becomes uncomfortable. It tells us the early universe had already done more than expected. Redshift is not only a measurement, it is a form of time travel. A high redshift galaxy is a photograph from a vanished era. We are not seeing what that galaxy looks like now. After more than 13 billion years, it may have merged with other galaxies, changed shape, grown larger, formed planets, fed black holes, or disappeared into a larger structure. The object Webb sees is not a current neighbor. It is a fossil of light, and yet that fossil is alive with information. It tells us what was possible when the universe was young. A redshifted photon is tiny, but its journey is enormous. It may begin near a young star inside an early galaxy. It travels outward through gas and dust. It leaves the galaxy. It crosses the expanding universe. Space stretches it. Galaxy clusters bend its path. Time weakens it. For billions of years, it moves through darkness without stopping. Then, finally, it reaches Webb. A mirror built by human hands catches it. An instrument records it. A scientist studies it. And a piece of the universe's beginning becomes known. There is something deeply human about this. We cannot go back to the first galaxies. We cannot send a spacecraft to cosmic dawn. We cannot stand beside the first stars or watch the first black holes feed. We can only wait for their light, and Webb is our way of waiting better. It catches the old messages we were never able to read before. But those messages are not always clear. They are stretched, faint, partial, and sometimes confusing. They arrive like letters damaged by time, written in a language we are still learning to translate. That is why Webb's discoveries feel so mysterious. The telescope is not handing us a complete answer. It is handing us ancient fragments, red smudges, spectral lines, faint glows, unexpected brightness, chemical hints, shapes in the dark. And from those fragments, scientists are rebuilding the first chapters of everything. The more Webb reads, the more we realize that the early universe was not a blank page. It was already marked with structure, energy, and transformation. Stars had already begun changing the chemistry of space. Galaxies had already begun assembling. Black holes may have already begun feeding. And inside that red-shifted light, Webb found another clue that the universe had been busy earlier than expected. Not only stars, not only galaxies, not only black holes, but dust and metals. The ashes of stars that should have needed time to live and die. But dust and metals. The ashes of stars that should have needed time to live and die. That is where the early universe becomes even stranger. Because in the beginning, the universe did not contain the rich chemistry we see around us today. There was no iron in the blood of living things, no calcium for bones, no oxygen for oceans, no carbon for cells, no silicon for stone, no gold, no silver, no dust grains drifting through newborn solar systems, no rocky planets waiting to form from heavy elements. The earliest universe was mostly hydrogen and helium with a little lithium. Simple ingredients. Light elements born in the first minutes after the Big Bang, before there were stars, before there were galaxies, before the universe had built the heavier pieces of itself. Everything heavier had to come later, inside stars. This is one of the most beautiful and unsettling truths in astronomy. Stars are not only lights in the dark, they are factories. Deep in their cores, under pressure and heat almost beyond imagination, atoms are fused into heavier atoms. Hydrogen becomes helium. In later stages of stellar life, heavier elements can form, and when massive stars die, they scatter those elements into space. A supernova is not only a death, it is a release. It throws newly made elements outward, enriching the gas around it. That enriched gas can later collapse into new stars, new planets, and eventually, in at least one place, living things. So when we see heavier elements in a galaxy, we are seeing evidence of previous stars. Stars that already lived. Stars that already died. Stars that had time to change the chemistry of their surroundings. That is why finding metals and dust very early in cosmic history matters. In astronomy, the word metal means almost anything heavier than helium. It does not only mean iron or copper. Carbon is a metal to astronomers. Oxygen is a metal. Silicon, nitrogen, neon, magnesium. All of them count in this language because they were not present in large amounts at the beginning. They had to be made by stars. Dust is also important. Cosmic dust is made of tiny solid grains, carbon, silicates, metals, and other compounds. It can form in the outer layers of stars, in the aftermath of supernova explosions, or in dense regions of space where enriched material cools. Dust blocks some light, glows in infrared, helps gas cool, and becomes part of the material from which planets can form. Dust is small, but it changes everything. A dusty galaxy is not chemically young in the purest sense. It has already experienced star formation and stellar death. It has already begun recycling its own material. It has already moved beyond the simplest stage of cosmic history. So when Webb looks very far back and finds signs of dust, metals, and chemical richness earlier than expected, it is finding evidence that the universe had already gone through several steps of transformation. First, stars had to form. Some of them had to die. Their elements had to spread. That material had to mix. New stars had to form from it. Dust had to appear. And all of this had to happen in a universe still very young. That is the pressure Webb puts on our timeline. The telescope is not only saying there are galaxies early, it is saying some of these galaxies may have already lived through enough stellar history to change their chemistry. And that is harder to explain. Not impossible, but harder. The first stars may have been massive and short-lived. If they were, they could have burned quickly and exploded quickly, enriching their surroundings faster than stars like the Sun ever could. A massive star can live only a few million years before dying. In cosmic terms, that is extremely fast. If the early universe formed many massive stars in intense bursts, then chemical enrichment could begin quickly. That may be part of the answer. The first generations of stars may have been brief, violent, and efficient. They may have flooded their young galaxies with radiation. They may have exploded as powerful supernovae. They may have left behind black holes. They may have seeded the surrounding gas with heavier elements sooner than expected. But the details are still difficult. How much dust could survive those violent explosions? How quickly could it form? How evenly could it spread through young galaxies? How much enrichment is needed to explain Webb's observations? Were early galaxies forming stars in a different way from galaxies today? These are not small questions. They affect the entire story of cosmic dawn, because the chemistry of a galaxy determines what comes next. With only hydrogen and helium, stars form differently. Gas cools differently. Clouds fragment differently. Massive stars may dominate. But once heavier elements and dust appear, the behavior of gas changes. It can cool more efficiently. It can form smaller stars. It can create more complex environments. Eventually, it can build planets. So early dust and metals are not only signs of the past, they are seeds of the future. They tell us when the universe began becoming capable of making places like our own. This is why Webb's ancient chemical clues feel so profound. They connect the first galaxies to everything that would come later. The carbon in life, the oxygen in water, the iron in planets, the dust in star-forming clouds. All of it begins with stars living and dying across cosmic history. If Webb finds that this process started earlier or happened faster than expected, then the universe may have become chemically rich sooner than we imagined. That changes the emotional shape of the beginning. The young universe was not only turning on lights, it was making ingredients. The first stars were not only shining, they were preparing the material for future worlds. Every supernova was a kind of ancient offering, scattering pieces of complexity into the dark. And somewhere in that long chain, billions of years later, those elements would become Earth. They would become oceans, mountains, cells, eyes, hands, mirrors, and a telescope named Webb looking back to find the first places where those ingredients began. There is something circular about that. The universe made the elements that made us, and we used those elements to build a machine that can watch the universe making them. But the more Webb sees, the more complicated the story becomes, because early chemical richness can make galaxies look different. Dust can hide young stars. It can redden light. It can make distant objects appear older, heavier, or more mysterious. It can confuse the measurement of mass and age. It can make a young galaxy look like an older one, or a nearby dusty galaxy look like a more distant object. So dust is both a clue and a trick. It tells us stars have already lived and died. But it also hides the truth behind a veil. This is why astronomers have to be careful. When Webb sees a red object, they must ask whether it is red because it is distant, because it is dusty, because it contains older stars, or because a black hole is affecting the light. The answer can change the entire interpretation. A galaxy that first appears impossibly massive might become less impossible once dust and star formation are understood better. A red dot that looks like an old stellar population might hide a black hole. A faint glow that seems simple might contain multiple sources tangled together. The early universe is not easy to read. It is layered. Light, dust, gas, stars, black holes, gravity, distance, and time all mix together before the signal reaches Webb. Still, the pattern remains. Webb is finding that the early universe was active enough to create light, structure, black holes, and chemistry sooner than many expected. Even when individual objects become less extreme after careful study, the overall picture stays exciting. The young cosmos was busy. More than a quiet beginning, it was a furnace, a place where the first generations of stars rapidly changed the darkness around them. A place where gas collapsed, stars ignited, heavy elements appeared, dust formed, and black holes fed. A place where the simple elements born after the Big Bang began transforming into the complex universe we inhabit now. That is why dust matters. A grain of cosmic dust is tiny, almost nothing. But in the early universe, it is a timestamp. It says, something has already happened here. A star has already lived. A star has already died. The universe has already begun remembering itself in matter. And when Webb finds that memory earlier than expected, it brings us back to the main question. Did Webb break our understanding of the universe? Or is it simply showing us that the beginning was richer, faster, and stranger than we knew? Did Webb break our understanding of the universe? It is a dramatic question, and it is easy to understand why people ask it. When James Webb began sending back images of ancient galaxies, distant red objects, early black hole candidates, and signs of rapid cosmic growth, the headlines became intense. Some said Webb had broken cosmology. Some said the Big Bang was in trouble. Some said the universe was older than we thought, or that everything scientists believed about the early universe had suddenly collapsed. Those headlines were powerful. They were clickable. They were emotional. But the real story is more interesting than that. Webb did not break the universe. It gave the universe a sharper voice. And that voice began correcting us. There is a difference between destroying a scientific theory and forcing that theory to become more detailed. A theory can be strong and still incomplete. A map can show the right continent and still miss mountains, rivers, forests, and dangerous coastlines. A model can capture the broad story of the universe and still struggle with the messy details of how the first galaxies formed. That is what Webb is revealing. Not that everything we know is wrong, but that the beginning was more complicated than our earlier instruments could show. The Big Bang theory is not based on one fragile idea. It is supported by many deep lines of evidence: the expansion of the universe, the cosmic microwave background, the abundance of light elements, and the large-scale structure of galaxies. Webb's discoveries do not erase those foundations. What Webb challenges are parts of the story that happen after the beginning. How quickly did the first stars form? How efficiently did early galaxies turn gas into stars? How did the first black holes begin? How soon did dust and heavier elements appear? How fast did small structures become bright enough to see? These are not small questions, but they are not the same as saying cosmology has failed. They are questions inside cosmology. Questions about the details of cosmic dawn. And details matter. Before Webb, scientists had models of the early universe. They used gravity, dark matter, gas physics, star formation, feedback from stars, black hole growth, and cosmic expansion to simulate how structure should form. Those models were impressive. They explained many things, but they were also limited by the data available at the time. The early universe was difficult to observe directly. It was distant, faint, redshifted, hidden behind time. So scientists had to make assumptions. Reasonable assumptions, but assumptions. How efficiently did early gas form stars? What were the first stars like? How much dust could form after the first supernovae? How quickly did black holes feed? How common were dense regions where structure could form early? Webb began testing those assumptions with real observations, and some of them began to bend. That is not a crisis in the dramatic sense. It is the normal, beautiful discomfort of science meeting better evidence. Still, we should not make the mystery smaller than it is. Some Webb observations genuinely surprised astronomers. Early galaxies appeared bright in large numbers. Some objects seemed compact and red in ways that were hard to classify. Some early black holes or black hole candidates seemed to imply rapid growth. Some distant galaxies showed signs of chemical enrichment and dust. The young universe looked busy. More than busy. Efficient. As if it had found ways to build structure faster than expected. At first, some objects looked almost impossible. A few early galaxy candidates seemed so massive that, if confirmed exactly as first interpreted, they would have caused serious tension with galaxy formation models. Scientists had to ask whether there was enough matter, enough time, and enough star formation to explain them. But then better data arrived. That is the part many headlines leave out. Some early claims softened under closer study. Spectroscopy confirmed some objects and revised others. Dust changed interpretations. Hidden black holes may have contributed to light that was first attributed entirely to stars. Gravitational lensing affected brightness estimates. Stellar populations in the early universe may have shone differently from modern ones. Measurements of mass and age became more careful. In some cases, what first looked impossible became merely surprising. But merely surprising is still important. Because even when the most extreme claims are corrected, Webb still leaves us with a young universe that appears more active than expected. The tension does not vanish completely. It changes form. It becomes less like a single impossible object and more like a pattern of unexpected efficiency. Galaxies forming stars rapidly, black holes growing early, dust appearing sooner, structures emerging quickly. Red compact objects resisting easy explanation. This is why the Webb story is stronger when we avoid exaggeration. The real universe does not need fake drama. The real mystery is already enough. A telescope designed to see the first galaxies is finding that the first galaxies may not behave the way our simpler models predicted. That is profound. Science is often imagined as a collection of facts, but science is more like a conversation with reality. We ask questions, we build instruments, we make predictions. Reality answers, but not always in the language we expected. Webb is one of the most powerful questions humanity has ever asked, and the answer is not, "You were completely wrong." The answer is, "You did not know the whole story." That may be more unsettling, because it means our understanding was not shattered, but humbled. The universe is still consistent. It still follows laws. But the way those laws played out in the first billion years may be richer than we knew. Maybe stars formed in more intense bursts. Maybe early gas clouds collapsed more efficiently. Maybe the first black holes started from heavier seeds. Maybe some galaxies became bright, not because they had impossible amounts of mass, but because their stars were unusually young, hot, and luminous. Maybe dust and active black holes made some objects appear older or heavier. Maybe our simulations need better treatment of feedback, gas cooling, radiation, and early stellar populations. Each of these possibilities keeps the universe understandable, but none of them makes it boring. This is the balance the script should keep. The word impossible belongs to the feeling, not the final conclusion. Webb detected things that felt impossible because they pressed against the timeline we had imagined. But in science, impossible often means something more specific. Impossible under the assumptions we were using. Change the assumptions, and the impossible becomes a clue. That is what Webb is doing. It is turning impossibility into information. A galaxy too bright tells us something about early star formation. A black hole too large tells us something about early growth. Dust too soon tells us something about the first stars dying quickly. Structure too early tells us something about gas flows, dark matter halos, and cosmic environments. The mystery does not disappear when we explain it. The explanation becomes the mystery's new shape. And perhaps that is why Webb feels so powerful. It reminds us that the beginning of the universe is not a finished chapter in a textbook. It is an active frontier, a place where every new observation can move the boundary between what we know and what we have only guessed. There is also something deeply human about this. We want certainty. We want the universe to fit our stories. We want the first galaxies to appear when our models say they should appear, and black holes to grow at the pace our equations allow, and dust to form only when the timeline feels comfortable. But the universe is not concerned with comfort. It formed the way it formed. It built what it built. And only now, billions of years later, are we receiving the evidence. Ancient light does not negotiate with us. It simply arrives. Webb catches it. Scientists study it. And slowly, our story changes. So did Webb break cosmology? No. But it cracked open a door we thought was only slightly open. Behind that door is cosmic dawn. Not as a simple, dim beginning, but as a violent and creative era where stars, galaxies, black holes, dust, and structure may have appeared faster than we expected. The terrifying part is not that science has failed. The terrifying part is that the universe still has entire chapters hidden inside its first light. And if Webb has already found so much complexity in the galaxies it can see, then we have to ask what came before them. Before the bright early galaxies. Before the little red dots. Before the first black holes grew large enough to reveal themselves. Before the ancient light Webb can clearly read. What happened in the dark before the first galaxies fully appeared? What happened in the dark before the first galaxies fully appeared? This is one of the most difficult parts of the story, because Webb can see far, but not infinitely far. Even the most powerful telescope cannot simply watch the Big Bang happen. It cannot see through every layer of cosmic history. It cannot reveal every moment directly. There are walls in time, boundaries beyond which light either has not reached us in a useful form or has been stretched, scattered, and hidden by the early universe itself. So when Webb looks back toward cosmic dawn, it is not seeing the very first instant. It is seeing the aftermath, the glow of things that had already begun. The first galaxies Webb observes are not the beginning of the beginning. They are already products of an earlier darkness. Something had to happen before them. Stars had to form. Gas had to collapse. Dark matter had to gather. The first black hole seeds may have appeared. The first heavy elements may have been made. The first radiation had to start changing the universe around it. And much of that chapter remains hidden. Before the first galaxies, the universe passed through a time often called the cosmic dark ages. The name sounds poetic, but it describes something real. After the universe cooled enough for atoms to form, there was a long period when space contained mostly neutral hydrogen and helium gas, dark matter, and faint radiation left over from the early universe. There were no stars yet, no galaxies shining, no planets, no dust, no familiar structures. The universe was not empty, but it was dark. Gravity was working quietly. Tiny differences in density, left over from the early universe, began to grow. Regions with slightly more matter pulled in more material. Dark matter gathered first, because it did not interact with light the way normal matter did. It formed invisible halos, gravitational wells where gas could collect. Inside those halos, hydrogen and helium began to fall inward. The gas compressed. It heated. It cooled. It fragmented. And eventually, somewhere in that ancient dark, the first stars ignited. We have never clearly seen those first stars. Not directly. They are called Population 3 stars, a name that sounds backward until you know the history. Astronomers named star populations based on the order they were discovered, not the order they existed. Population I stars, like the Sun, are relatively rich in heavy elements. Population 2 stars are older and poorer in heavy elements. Population 3 stars would be the first generation, made from almost pure hydrogen and helium with almost no metals at all. They may have been unlike any stars we see today. Without heavy elements to help gas cool and fragment into smaller pieces, early star-forming clouds may have produced enormous stars. Some may have been hundreds of times the mass of the Sun. They would have burned extremely hot, lived very short lives, and died violently. Their light may have helped end the cosmic dark ages. Their deaths may have seeded the universe with the first heavier elements. Their collapsed cores may have formed some of the first black holes. If Webb is seeing surprisingly early galaxies, early dust, and early black hole activity, then these first stars become even more important. They are the missing ancestors, the invisible generation whose lives and deaths shaped everything Webb is now detecting. Maybe the first stars formed earlier than we thought. Maybe they formed in greater numbers. Maybe they were more massive. Maybe they produced heavy elements faster. Maybe they left behind black holes large enough to grow into the early monsters Webb hints at. This is why the darkness before the first galaxies matters so much. It is not empty background. It is the workshop, the place where the universe prepared the tools it would later use to build galaxies. There is another process happening during this era: reionization. The word is technical, but the idea is beautiful. After atoms formed, much of the universe was filled with neutral hydrogen gas. This gas could absorb certain kinds of light, making the universe foggy in a cosmic sense. When the first stars and galaxies began shining, their energetic radiation started breaking electrons away from hydrogen atoms. Slowly, the fog cleared. The universe became transparent to more kinds of light. This transition is called the epoch of reionization. It was not instant. It happened in patches. Around the first stars and galaxies, bubbles of ionized gas formed. These bubbles grew, overlapped, and eventually filled much of space. The first sources of light were not just shining into darkness. They were changing the darkness itself. They were clearing the universe. Webb is trying to study the galaxies that helped do this. By finding very early galaxies and measuring their light, astronomers can ask whether they produced enough radiation to reionize the universe. Were small galaxies the main drivers? Did early black holes help? Did massive stars flood space with ultraviolet light? How quickly did the fog lift? Again, the answers are still forming. But Webb is showing that early galaxies may have been more numerous and active than expected. If there were many small, bright galaxies forming stars efficiently, they may have played a major role in clearing the cosmic fog. That means Webb's impossible discoveries may connect to one of the largest transformations in cosmic history. The universe went from dark and foggy to transparent and illuminated, from hidden structure to visible galaxies, from neutral gas to a universe where light could travel freely across immense distances. And somewhere in that transition, the first stars, galaxies, and black holes wrote the opening lines of everything that came after. This is why cosmic dawn feels so haunting. It is the universe's first morning, but not a gentle morning, more like a storm breaking through night. Stars igniting in dense pockets of gas, radiation carving bubbles into hydrogen fog, supernovae blasting heavy elements into young space, black hole seeds forming in collapsed remnants or collapsing clouds, small galaxies flickering into existence, merging, growing, and feeding the first cosmic web with light. By the time Webb sees some of these galaxies, the story is already underway. And if those galaxies look bright, dusty, massive, or structured earlier than expected, then something in the unseen chapter before them must have been powerful. Something set the stage quickly. Something allowed the first systems to grow fast. Something made the young universe more efficient than our earlier models imagined. That something may not be one single process. It may be many. Dark matter halos forming in dense regions. Gas cooling under early conditions. Massive first stars living short lives. Direct collapse black holes forming heavy seeds. Rapid mergers. Intense bursts of star formation. Radiation clearing the fog. Supernovae creating dust and metals faster than expected. All of these forces may have worked together, not neatly, but violently. A universe becoming complex in the dark. And because we cannot see every part directly, we reconstruct it from clues. An early galaxy is a clue. A little red dot is a clue. A distant black hole is a clue. A trace of dust is a clue. A spectral line is a clue. A redshift is a clue. Webb is not giving us a complete film of the first billion years. It is giving us fragments of a lost beginning. And from those fragments, scientists are trying to rebuild the hidden machinery of cosmic dawn. This may be the most important thing to understand about Webb's discoveries. The telescope is not only showing us objects, it is showing us consequences. If a galaxy is already bright, something made it bright. If a black hole is already massive, something seeded and fed it. If dust is already present, stars already lived and died. If structure is already visible, gravity and gas had already been organizing matter. Every surprising object points backward to an earlier process. Every impossible-looking discovery asks what happened before the light we see. And that is why the title of this journey matters. James Webb did not just detect something impossible in the simple sense. It detected evidence that the early universe has a missing chapter. A chapter we cannot yet read directly, but can feel through the pressure it leaves on everything Webb observes. The first galaxies are not the first page. They are the first page we can clearly see. Behind them are pages still stuck together in darkness, and with every deep observation, Webb is gently pulling them apart. Not quickly, not completely, but enough to show that the beginning was not as empty, slow, or simple as we once imagined. Before the first galaxies fully appeared, the universe was already becoming something. The dark was already moving. The first lights were already preparing. The first engines were already forming. The first elements were already being forged. And now, billions of years later, we are catching the faint result of that hidden work. This brings us to the final thought. Maybe the impossible thing Webb detected is not one galaxy, one red dot, one black hole, or one patch of ancient dust. Maybe the impossible thing is the missing chapter itself, the unseen era where the universe learned how to become complex before we expected it to. Maybe the impossible thing is the missing chapter itself, the unseen era where the universe learned how to become complex before we expected it to. By the time James Webb sees the early galaxies, the story has already begun. That is the strange thing. We call them first galaxies, ancient galaxies, galaxies near the beginning of time, but even they are not the true beginning. They are evidence that something earlier has already happened. A galaxy shining in Webb's mirror is not a starting point. It is a result. Something gathered the dark matter. Something pulled in the gas. Something cooled it. Something formed the first stars. Something caused those stars to die. Something made the first heavy elements. Something produced dust. Something seeded black holes. Something allowed young galaxies to become bright enough to be seen from more than 13 billion years away. And the deeper Webb looks, the more that hidden something matters. Because if the early galaxies were faint, simple, and rare, then our old picture would feel comfortable. The universe would have grown slowly. Darkness would have lifted gradually. Stars would have formed, galaxies would have assembled, black holes would have grown, and everything would fit neatly into the timeline we expected. But Webb has made that timeline feel less neat. Not broken, not destroyed, but pressured, stretched, humbled. The young universe appears to have been more active than expected. Some galaxies are brighter. Some objects are redder and stranger. Some black holes may be larger or more common than we thought. Some systems show hints of dust, chemistry, and structure earlier than expected. Even when individual discoveries are revised, the larger feeling remains. The beginning was busy. That is what Webb keeps telling us. It was not an empty stage waiting calmly for the first actors to arrive. It was already full of motion behind the curtain. Gravity was gathering matter. Gas was falling into invisible wells. Stars were forming in dense pockets. Radiation was burning through darkness. Supernovae were scattering the first heavy elements. Black holes were feeding in places too small and distant for us to understand easily. The universe was young, but it was not simple. That may be the most important lesson. Human beings often imagine beginnings as clean. A first page, a first step, a first light in darkness. But nature rarely begins so neatly. The beginning of a forest is not just one seed. It is soil, rain, fungi, decay, sunlight, insects, and old minerals. The beginning of a civilization is not just one city. It is language, memory, rivers, climate, tools, hunger, fear, and cooperation. The beginning of a galaxy may not be one bright moment either. It may be a storm of causes, and Webb is seeing the aftermath of that storm. This is why the phrase "something impossible" works emotionally, even if science must treat it carefully. Webb has not found magic. It has not found proof that physics is wrong. It has not made the universe irrational. Instead, it has found objects that looked impossible under our earlier expectations. And that is where discovery begins. An impossible object is often a message from reality saying, your story is missing a page. The page might contain heavier black hole seeds. It might contain more efficient early star formation. It might contain massive first stars dying quickly and enriching space faster than expected. It might contain dense regions of the cosmic web where galaxies grew unusually fast. It might contain dust and hidden black holes fooling our first estimates. It might contain physics we already know behaving in extreme conditions we have not fully modeled. Or it might contain something we have not thought of yet. That possibility is always there. Quiet. Uncomfortable. Beautiful. Because every time humanity builds a better eye, the universe becomes less familiar. Galileo turned a telescope toward Jupiter and found moons moving around another world. Hubble looked into dark patches of sky and found galaxies everywhere. Webb looked toward cosmic dawn and found a beginning that seems richer than expected. This is how the universe teaches us, not by giving us the answers we want, but by showing us where our questions were too small. Before Webb, we thought we had a reasonable outline of the early universe. And we did. Darkness, first stars, first galaxies, reionization, growth, mergers, chemical enrichment, black holes, larger galaxies. That outline is still there. But now, Webb is filling it with details that do not sit quietly on the page. They move. They disturb. They ask for more room. The first billion years may have contained more variety than expected. Some regions may have stayed faint and simple, while others raced ahead. Some galaxies may have formed stars in violent bursts. Some black holes may have started with unusually large seeds. Some dust may have formed quickly in the deaths of massive stars. Some early systems may have looked mature, not because they were old in the way we think, but because the young universe had different ways of becoming bright. This does not make the universe less understandable. It makes it more alive. A simple universe is easy to describe, but the real universe has never promised simplicity. It is layered. It is uneven. It makes exceptions. It forms rare objects. It lets some regions evolve faster than others. It hides power inside faint red dots and history inside tiny grains of dust. And Webb is only beginning. That may be the most humbling part. The telescope has not finished the story. It has barely started reading. More observations will come. Some early mysteries will become ordinary once understood. Some impossible-looking objects will be reclassified. Some dramatic claims will fade. Other discoveries will become stronger. New ones will appear. The map will change. Again and again. That is not weakness. That is the life of science. A universe that can still surprise us is a universe we are still honestly studying. So what did James Webb really detect? Maybe it detected galaxies that formed earlier than expected. Maybe it detected black holes growing too quickly. Maybe it detected dust and metals too soon. Maybe it detected compact red objects that do not fit easily into our categories. But beneath all of that, Webb detected something deeper. It detected the boundary of our understanding. It showed us the place where the known timeline becomes uncertain, where models turn into questions, where ancient light arrives carrying more history than we expected it to hold. It detected a missing chapter of time, a hidden era between the dark beginning and the galaxies we can clearly see. A chapter where the first stars burned, the first black holes formed, the first heavy elements were scattered, the first dust grains drifted, and the first galaxies began assembling faster than our old story allowed. We are not reading that chapter directly yet, not fully, but we can see its shadow. We see it in galaxies that shine too brightly, in red dots that hide too much power, in black holes that grew too soon, in dust that remembers stars already dead, in structures that seem too organized for their age. Each one is a clue pointing backward. Each one says, Something happened before me. And maybe that is the real gift of Webb. It does not only show us what is visible, it teaches us to feel the weight of what is still hidden. The universe began in darkness. Then, somehow, the darkness learned to make stars. Stars learned to make elements. Elements learned to make dust and planets. Planets, at least once, learned to make life. And life, on one small world, learned to build a golden mirror and send it into space to ask what happened before any of us existed. Now that mirror is far from Earth, cold and silent, catching ancient light one photon at a time. And in that light, the universe is whispering something we are only beginning to understand. The beginning was not simple. The first chapters were not empty. And the story of how everything became everything is still unfinished. So tonight, as Webb keeps watching from the darkness beyond Earth, we are left with a quiet thought. Maybe the impossible is not something that breaks the universe. Maybe the impossible is what the universe calls us when our imagination has not yet caught up. And somewhere, in the faint red light from the edge of time, the missing chapter is still waiting to be read.